In this chapter, chapter 4, we'll be talking about Euclidean geometry, which is the geometry that you probably studied at least a little bit in high school. Here are some of the topics we'll talk about, but we're going to begin with some definitions that we'll be using. So, first of all, if you have two distinct lines, L and M, if those lines are parallel, or let me say they are parallel, which is written like this, L, then looks like two parallel lines, M. Line L is parallel to M. If and only if, that's what the IFF means, if and only if, well, the first thing is they have to lie in the same plane in order to be parallel. And then they also cannot intersect. We all know what parallel lines look like. If they're in the same plane, like on this piece of paper, that's one. That could be a second line. Those two lines, I made them look pretty close to parallel. In theory, they will never intersect. Okay, the next definition is a line that intersects two other lines. We're going to call that a transversal. And we've got several examples here for which we are going to learn some other terms. These are the two unlabeled lines are the lines we start with, and then the transversal is the line in my pictures going downward through the other two lines. So given that T, here's the line T, is a transversal of the other two lines, mark the angles that are described or listed here. Alternate interior angles. We have two choices. The interior means they're going to be between the two original lines, and alternate means they're going to be one on one side of the transversal and one on the other side. They're going to alternate, so to speak. So here is one pair, that and that. Those two angles are alternate interior. I also could have picked, instead of those two, I could have picked this angle and this angle for alternate interior angles. In the second one, we're going to mark corresponding angles. So they are going to be on the same side of the transversal. And again, I have several choices here. I actually maybe have 4 different ways I could draw this picture. I'll put one here and then one of them here. Those two angles that I marked are corresponding angles. They're on the same side of the transversal and they are underneath the two lines. So I could have put them one here and here for corresponding angles. I also could have gone above. I could have gone here and here, or here and here, with corresponding angles. The third one is going to be interior angles that are on the same side of the transversal. Well, it's kind of long, but it's very easy. It explains exactly what I'm looking for. The interior angles, the two, would be this one and this one. They're on the same side of the transversal. They're on the left side of it in my case. And they are both interior to the inside the two original lines drawn. Now, I could also have done for interior angles on the same side of the transversal, I could have done this angle and this angle as well. All right, well, let's take a look at number 4. The absolute parallelism theorem. Well, it says that given two lines, L and M, that are cut by a transversal T, and we have a picture here, here's line L, here's line M, and they're cut by transversal T. If a pair of alternate interior angles are congruent, then the lines are parallel. Well, I've drawn two alternate interior angles, angle 2 and angle 1. I very easily could have chosen this one and this one. The proof would be similar. Okay, and I labeled this point where the first intersection up here and the second one down here, that's going to be point A and that's going to be point B. All right, so as we've shown in the diagram, suppose the alternate interior angles are 1 and 2. Suppose they are congruent. Well, what does that mean we have to prove? If a pair of alternate interior angles are congruent, then the lines are parallel. We have to prove that the two lines L and M are parallel. Well, we're going to do a proof by contradiction here. FTSOC stands for the sake of contradiction, let's assume that lines L and M are not parallel. And then we'll reach a contradiction, which implies that this statement is false. That would show that L is parallel to M. So for now, for the sake of contradiction, assume the lines L and M are not parallel. Well, by the definition of parallel, if they are not parallel, they're going to have to intersect at a point. So, by definition, they meet at a point. And let's call R the point where they meet. So R is the point, the intersection of the two lines. And here we're going to draw the point of intersection above. So let's do it this way. Let's extend this and extend this, those two lines, and say this is our point R where the two lines intersect. Okay, well, now notice that angle 2 is an exterior angle to one of the triangles that we just created, this triangle. So I'll call that ABR, triangle ABR. What do we know about exterior angles to a triangle? The exterior angle, the measure of angle 2, is bigger than both of the opposite interior angles, this angle and this one. So specifically, I'm just going to say the measure of angle number 1. Because it's an exterior angle, we know that the measure of angle 2 is bigger than the measure of angle 1. And how do we know that? That was by the exterior angle inequality theorem. Exterior angle inequality theorem. THM for theorem. Well, this is a contradiction because we were given that angle 1 and angle 2 are congruent. So how could measure of angle 2 be greater than the measure of angle 1? This is a contradiction. Therefore, the statement we assumed to be true for the sake of reaching a contradiction is false, which means that L must be parallel to M. Okay, well, to finish up this video, let's write the converse of the absolute parallelism theorem above. All right, well, what does it say? The converse is going to be, this one was if a pair of alternate interior angles are congruent, then the lines are parallel. The converse is if the lines are parallel, then the alternate interior angles are congruent. So, given two lines L and M cut by a transversal T, if the two lines are parallel, L is parallel to M, then alternate, I'm going to abbreviate that ALT, interior, I'm going to abbreviate that INT, angles are congruent. This statement, it is believed that this statement cannot be proven. And it's called the Euclidean parallel postulate. And in Euclidean geometry, we simply assume that this statement is true.